So good afternoon. My name is Andrew Keller. I'm currently at the Painter Group at Caltech, but the work I'm speaking about today was done during my PhD in David Goldhaber-Gordon's group at Stanford University. So the work was sort of about cast in a general light as studying quantum phase transitions in a controllable setting, and specifically we wanted to study the crossover from a quantum critical state realized by the two-channel Kondo effect to a more conventional Fermi liquid state with comparisons to exact analytic expressions for conductance, which we'll measure and transport. So before I get on with it, I'd just like to take one slide to sort of introduce what I'm doing now in my postdoc. It's not pertinent to the rest of the talk, but just as an example, I'll be talking about quantum dots most of the time in the talk, but right now what I'm currently working on is interfacing superconducting qubits with mechanics. And so this is just a sample of some of the work going on in the Painter Group right now. We can make superconducting qubits on silicon membranes. We can pattern lumped element circuits with e-beam lithography to realize kind of band gap structures to which we can couple these qubits. And we can also couple qubits to very high quality mechanical resonators. So pictured here is a mechanical resonator in an acoustic band gap. It's a 5 gigahertz resonance, and it has a quality factor of about 50 billion, which is astounding. And you can kind of imagine the possibilities if we were able to actually interface superconducting qubits with mechanical resonances of that high quality factor. So if you're interested in this sort of thing, tangentially or directly, please do talk to me after the talk, and I can go into further detail about what I'm up to now. So without further ado, I'll begin this talk by kind of giving an outline, and I'll begin by saying some words about the Kondo effect, quantum phase transitions, and tunable quantum dot systems. And then I'll get into more details. What we'll be studying is the two-channel Kondo effect. And I'll kind of provide it in the context of a prototypical non-Fermi liquid state. And then while this state has been seen before, what hasn't been done is to kind of study experimentally and compare to analytic expressions for the crossover between this quantum critical behavior in the non-Fermi liquid state and the more conventional Fermi liquid states. And then I'll try and give some perspective on where I think this could go in the future. So I'm sure I'm not going to belabor the point. Many people in the room are familiar with the Kondo effect, but it occurs when you have some sort of local moment that is coupled to itinerant electrons. And at high temperatures above some characteristic energy scale, the Kondo temperature, you just sort of have incoherent spin flip scattering off this impurity. And as you lower the temperature below this Kondo temperature, you eventually form a many-body singlet state where the itinerant electrons collectively screen out this local moment such that at t equals 0, you have s equals 0, a spin singlet state. And it's interesting in general, I think, to theorists because it's a problem that can be attacked from so many different theoretical techniques. But also to experimentalists, it describes a great number of situations. It's kind of relevant whenever you're looking at the low energy physics of the Anderson impurity model. More exotic Kondo effects may be thought to be related to some material systems. Without overstating the connection, I think you could make a case that heavy fermion systems, where you have some lattice of magnetic moments interacting with conduction electrons, that's sort of related to the two impurity Kondo effect. The heavy fermion systems have this anomalously large effective electronic mass, and that's due to the hybridization of your conduction electrons with these magnetic impurities. And in the two impurity Kondo effect, you could kind of consider this to be like a prototypical model in the sense that if you have two impurities, they could if you have some large inter-impurity coupling, they could kind of form a singlet on their own. Or if the coupling of each impurity to an electronic reservoir is stronger, then you could essentially just have each impurity screened out by the Kondo effect with its own reservoir. And so there's some kind of competition depending on the strength of this inter-impurity coupling strength between what the ground state is, and it turns out there's a critical point in between. So I'll be talking about a related two-channel Kondo effect, for which I would say the direct analogy with a real material system of great interest is not quite as clear. But actually, at the end of the day, the two-impurity Kondo effect and the two-channel Kondo effect are deeply related, and I can kind of go into that in one-on-one conversations if you'd like. The system we're going to use to realize this effect is a quantum dot in a gallium arsenide heterostructure. Kind of a, I think these have been around for quite a while now, so the bar to do new things with them gets higher all the time. But you can kind of pattern very complicated devices using electron beam lithography to define gate electrodes on the surface of these heterostructures. When you apply voltages to these gate electrodes, you can selectively deplete an electron system, a 2D electron system, hosted at the interface between the aluminum gallium arsenide and the gallium arsenide. And in so doing, you can kind of carve out regions that are isolated kind of apart from some tunnel couplings to their own reservoirs, and these are our quantum dots. And these can host anywhere from 0 to tens or in some cases hundreds of electrons depending on the size of the quantum dot and so on. So here I'm just showing a double quantum dot system that we studied for many years in our group. Originally, we had the idea of studying a kind of Kondo effect where you had both spin and charge degrees of freedom in this picture. But it turned out later, I thought I'd just mention this since it's relevant to a lot of people in the room, I think. We used the same device not to study the Kondo effect, but to study a kind of a co-tunneling drag effect in which a voltage bias across one of the two dots could be observed to induce a current flowing in the dot that's side coupled to it. And that was work done with David Sanchez and Rosa Lopez, who are both here today, of course. So I'll describe now this two-channel Kondo effect. Perhaps it seems a bit obscure. Maybe you haven't heard of it before. The basic idea is if I have just a single impurity spin, and I'm going to couple that to two reservoirs. And you might think, well, we do this all the time. If you have a quantum dot and you couple it to two leads such that you can measure transport, isn't that what I'm describing? And I would say, no. Actually, in that configuration, usually what happens is you can think of even and odd combinations of your two leads, and only one of those will actually couple to the dot. So what I'm describing here is a little different. It's a single impurity that is coupled to two electronic reservoirs, except the reservoirs are not allowed to exchange charge with each other. So maybe I'll describe this a little more clearly by way of analogy. Suppose you have an employee of a company, and the employee has two bosses, okay? Now, if one boss is more important than the other, maybe you might think that at short time scales, it's hard to know who to answer to if they have different opinions. But at longer time scales, or we should say at lower energies, then ultimately you answer to one of these bosses at the end of the day. And likewise, if the two bosses talk to each other, the more they talk to each other, the less likely there is to be some conflict. But if they're totally isolated from each other, then that sets you up also in a frustrated situation. In other words, what I'm trying to do is summarize the relevant perturbations to the two-channel Kondo state, and I've just kind of given you two of them by way of analogy. The exchange coupling detuning from this impurity spin to each of the two reservoirs needs to be the same to realize this two-channel Kondo effect. It's kind of a frustrated state. And likewise, you need to suppress charge transfer, or in other words, you don't want these two reservoirs to talk to each other. And if you have either of these things, then at t equals 0, you no longer have this two-channel Kondo state, but rather a more conventional Fermi liquid state, like the impurity is, say, Kondo screened by the more strongly exchange-coupled reservoir, something like that. And you can also use a magnetic field to kind of disrupt this two-channel Kondo state. So experimentally, it seems difficult to get a handle on all these relevant perturbations and set them equal to 0. But you can do it in specially engineered systems. And I'll describe a little bit more as we go on. Why is this interesting? Well, there are a number of things you can read in the theoretical literature that, as an experimentalist, we would like to be able to address. I think, actually, earlier, just in the previous talk, Yigal Meir alluded to this. There's a kind of a t equals 0 residual impurity entropy of 1/2 log 2, which is kind of peculiar. It would be really nice as experimentalists if we could measure that. But so far, that has been elusive. That's associated, supposedly, though I won't make any experimental claim to this, with free Majorana fermion local to the impurity site. As I sort of alluded to earlier, the two-channel Kondo fixed point is identical to the two-impurity Kondo fixed point up to some trivial terms. And so when we study one system, we kind of know something about the other, at least in a theoretical way. And supposedly, when you have incoming electrons, you can imagine kind of firing them at the impurity. They supposedly scatter off into collective excitations. So I guess what I'm trying to say is, if you read the theoretical literature, there's a lot of interesting things about the two-channel Kondo state. What's sort of frustrating to the experimentalist is that what we can measure is conductance. So it's not clear how much of this we can actually prove out by doing conductance measurements. However, it certainly seems like a good idea to try our best to corroborate the theoretical predictions with experimental signatures in the conductance, such that we can at least believe for sure that we're realizing the two-channel Kondo state in an experiment. All right, so getting back to the Hamiltonian I showed you. Turns out all the relevant perturbations to the two-channel Kondo state can be written in this form, but for somewhat technical reasons, we're just going to focus on this exchange coupling detuning, which we can achieve by tuning the gate voltages of our quantum dot. As we, I guess it's important to realize that this is actually corresponding to a second-order phase transition. There's some, if you look in your favorite textbook of quantum phase transitions, usually associated with these phase transitions, you have some energy scale that goes to 0 at a critical point. You have some parameter that you can tune, and there's some critical exponent that is characteristic of the system you're studying, which is the same on either side of the phase transition, although the prefactor might, differ and be non-universal. The critical exponent is a universal property of the phase transition you're looking at. And there's associated length scales as well that have their own critical exponents. I am reiterating that to just tell you that in the case of the two-channel Kondo effect, this has all been calculated and is known, so we can try and compare the results of experimental measurements to the predictions for this crossover behavior, provided we have some way of extracting this characteristic energy scale from the conductance measurements. Okay, so how are we actually going to implement this? The way to make the two-channel Kondo state when you have a spin impurity was described first in this theoretical paper. Essentially, consider a single quantum dot coupled to two leads such that you can make transport measurements. And then also side couple this quantum dot to what we'll term a metallic grain. We call it that because it's a grain implying that it's small enough that it has a charging energy that is much larger than temperature, and large enough, however, that it looks metallic in the sense that the level spacing is roughly temperature or less, such that it looks like a kind of continuous density of states. And when you do that, you've kind of set up the interesting condition where, because of the Coulomb interaction on this grain, at least to the lowest order, you can't really exchange an electron between the grain and the leads because the grain is Coulomb blockaded. You can, however, still have spin flips. And so the net result is that you suppress charge transfer between the grain and the leads quite highly, so that the leads form one reservoir for this impurity, and then this grain forms another reservoir. So in other words, I've set up the situation I described for the two-channel Kondo effect. If you want to see how this relates to the device, so in here, this is a large quantum dot. It probably has hundreds of electrons on it, and it will serve as our metallic grain. It's side coupled to this small quantum dot here, and then I have two leads with which I can measure transport. So that's the situation. This is just how we implement two-channel Kondo effect, but you can do sort of a pseudo-spin impurity where you look at two charge states of an actual metallic grain. And this was also very impressive realization of two-channel Kondo physics coming from Frederick Pierre's group. And there are related quantum phase transitions that claim to probe quite similar physics when you have a resonant level, say from a carbon, I guess this should say nanotube, carbon nanotube that is coupled to dissipative leads. And again, this is kind of all related quantum critical scaling behavior that you can see in nanostructures. All right, what's been seen in the past from the group I was in is only the quantum critical behavior. So try and tune your relevant perturbations to 0 and look at what you get as a function of drain source bias voltage, temperature, and what you should see is, some characteristic scaling collapse. So basically, if you plot the measured conductance through the small dot here in a special way, which you can see just by how the axes are presented, then there's a universal scaling behavior, and the measured experimental data are supposed to collapse on top of some curve. And this is characteristic of the quantum critical point. What hasn't been seen, or at least quantitatively mapped out, is how as you change the exchange coupling detuning, you go back from this quantum critical scaling into more conventional Fermi liquid behavior at low temperatures. So that's sort of what I was doing. This is the device we made. It's more complicated than it needs to be for the experiment because initially we had tried to do a different experiment involving interferometry in the two-channel Kondo state, which I'll kind of talk about at the very end. But it's just another angle on the kind of picture I showed you previously. As you can see, actually, it's kind of a nightmare to measure this thing because you have like at least 10 different gate voltages. When you cool this down in your dilution refrigerator and you have to tune up two of these quantum dots, you have a lot of axes to play with, and these being standard lock-in measurements of conductance, they take a little while, even just to get simple 2D color plots. So if you want to try and identify the two-channel Kondo state on your own, it's a little bit difficult. So we teamed up with some theoretical collaborators, Gergely Zoran, Pascu Moka, and Irek Weyman, and they're able to produce plots of conductance measured in equilibrium as a function of, on the left axis here, the gate voltage for the metallic grain or the big dot. I'll use those terms interchangeably. And the gate voltage for the small dot. So right in the center here, if I were to make a vertical cut, that's when I have one electron on the small dot, and then I can deplete it or add another electron by going to either side of this plot. And it turns out, kind of strangely, that there's not a quantum critical point in this particular model, but actually quantum critical lines. So there's a continuous line as a function of gate voltage on the small dot and the big dot, where using numerical or normalization group calculations, you can identify two-channel Kondo behavior from the finite size scaling. That was a little bit surprising to us, but one interpretation you can make of this is that at the center of this line where there's one electron on the small dot, this is a kind of a spin-like two-channel Kondo effect, whereas as you move away from the center, somehow it transitions continuously to a more charge-based two-channel Kondo, generate charge states of the grain. I think it's hard to say experimentally we have corroboration of that yet, but the calculations at least supposedly seem pretty clear. All right, so what we can do then is, knowing that we should see these lines, the strategy to identify the two-channel Kondo state will be to just park our small dot gate voltage and take a cut as a function of the large dot gate voltage. And we should run into one of these two-channel Kondo lines if we do that. And you know, if you look at the left, the plot looks a little different than what I just showed you. It looks kind of slanted. The reason for that is that in an experimental system, you don't actually have independent axes. You know, as I change the gate voltage on the small dot, I might also be gating the large dot at the same time. And so you kind of have to calibrate out those capacitances, or, you know, do the reverse and have your theorist try and match your experimental data by distorting the data suitably. And, you know, but that can be done based on measurements of the capacitances. So when you do that, you see that if I park here, I should see a scaling collapse of the temperature-dependent conductance. And if we do the same in the experiment, we sort of see a good collapse. At least it looks pretty good for one sign of the drain source bias voltage. The other sign doesn't quite work as nicely. But you know, interestingly, in the NRG calculations of the conductance, it's not quite a perfect scaling collapse either. Nonetheless, they say that the finite size scaling does show characteristic signatures of two-channel Kondo behavior at this point. So we'll say, okay, let's just presume that this is indeed the two-channel Kondo state. What would be more compelling is if we had some knob we could tune, now that we've supposedly reached this two-channel Kondo state, to show something that agrees well with predictions for how this crossover should happen. As we tune away from the quantum critical behavior, this should be done in a way that agrees with the exact expressions which are available. So before I get to that, this black line here, this does come from a kind of gross looking but nonetheless exact expression which you can relate to conductance in the limit where one of my leads for my small dot is much more weakly coupled to the small dot than the other one. And so this is the limit in which I'm looking at equilibrium conductance, but I can sweep the voltage on the weakly coupled lead and use that to kind of probe the density of states. So kind of in analogy to how an STM operates, we can look at finite energies without driving the system out of equilibrium. And so long as we do that, the conductance relates very simply to this expression. And that's basically what gives us this black line here onto which these points should collapse. Now, when we look a little bit away from this line, say by tuning the big dot gate voltage a little bit, we still have a scaling collapse at high temperatures. But below some characteristic temperature, which I called T star on an earlier slide, you start to get very dramatic deviations from this scaling collapse. And these deviations correspond to the crossover to the Fermi liquid state that happens as you go low in temperature. And these deviations can also be fit to exact expressions given by here, this expression here. And it's just a function of this T star parameter. So no matter if I'm doing exchange coupling detuning or if I had changed the magnetic field, all of that just gets rolled up into this effective T star parameter here. So it's kind of interesting. And you know, it's again a signature that this is kind of a universal property of the model. We can take both of these expressions and in particular using the exact crossover expression on the previous slide, try and extract what this T star is as a function of the gate voltage on the large dot. And somewhat unsurprisingly, as I add one electron, it's not so different from adding 2 electrons to the large dot. There's already hundreds of electrons on it, so it shouldn't really matter intuitively. So we do see this kind of periodic behavior here. And as I mentioned earlier, this T star parameter should go kind of quadratic in the difference in exchange couplings. We can just, I think it would be a bit of a reach to try and claim that we can back out some quadratic dependence here. But if we just try and see how well these points fall onto a parabola, that's what's plotted here. And we're allowed to have different prefactors on either side of this critical point in accordance with kind of standard theory of quantum phase transitions. So that's what this middle row is showing. On the left, you have our experimental data. This is drain source bias voltage on the vertical axis and large dot gate voltage on the horizontal axis. And this is sort of the mock-up from NRG calculations of what we expect to see. There's this third row down here, which I find to be a little less intuitive, but it turns out there's also a scattering phase that enters into the problem. I plot it because you can back it out of our theoretical fits, but I don't think it has as nice of an interpretation as this T star, in the sense that, if you want to draw a close relation to the theory of quantum phase transitions, this is the kind of characteristic energy scale for the crossover.
How do you measure the phase shift?
Yeah, so it comes from this somewhere in here. I believe this S part here has some phase built into it. And you can also see it if you're actually at if you're actually at this critical point, it also shows up into here. And so you need to, in general, account for that as a fitting parameter. Okay. So, but it does come from fits. It's not a direct experimental measurement. All right, so I guess that's the state of the experiment so far. It's nice that we can do conductance measurements and see a pretty good, or at least plausible correspondence between what's been calculated from conformal field theory to be exact analytic expressions. It maybe gives us some confidence that we are realizing a two-channel Kondo state, even though so far no one has been able to probe the more interesting direct properties of the non-Fermi liquid state, like this 1/2 log 2 entropy, which quite obviously characteristic of the non-Fermi liquid state. So what we had intended to do with this experiment was to actually try and do some Aronoff-Bohm interferometry. So this has sort of a long history now in gallium arsenide quantum dot systems, kind of becoming increasingly sophisticated over time. And so we had hoped to kind of do the same game here. The idea is really you have some two-path interferometer, and you should see interference fringes as you tune magnetic field by small amounts. Small enough that you don't significantly drive yourself away from the two-channel Kondo state, but large enough that you can actually see a few fringes and get a good fit for the phase, the transmission phase. I would say that this did not work very well for the technical reason that, unfortunately, as you try and tune the magnetic field to see interference fringes from the Aronoff-Bohm effect, what you also do is change the tunnel couplings in a kind of unpredictable way. And so therefore, you drive yourself away from the two-channel Kondo state in a way that you don't understand. I think we'd still like to try this sort of a measurement. We tried it. It sort of showed some interesting behaviors, but I'd say in general, the visibility of the interference is unreliable, and so we need to basically update this in accordance with more sophisticated electron interferometers that have been developed since we first started this study. And so currently we have, still this question, we'd like to do something beyond conductance measurements. It's not clear exactly what that should be, but perhaps we can at least try interferometry, since people have demonstrated this works even with Kondo states. And so currently in the group, we're trying to fabricate devices analogous to what's been done with just a single quantum dot, but by side coupling this single quantum dot in this modified interferometer to a large quantum dot down here to try and realize the two-channel Kondo state, again, in an interferometer that actually works. Okay, so with that, I'd just like to acknowledge all the people that did great work on this. I worked with graduate student Lucas Peters on this experiment and was mentored by Sami Amasha and Ileana Rao. And I think the energy calculations were really critical to the success of this experiment. So I'd like to, again, thank my collaborators, and thanks for your attention.
Thank you.